Great. Thank you all for coming back after lunch. So we will continue with the talk by Andrew Cross of IBM, who will tell us about scheduling syndrome measurement circuits. Please take it away.
Yeah, thank you very much. Thanks for inviting me. And it's a pleasure to be here in person with everybody. Yeah, so I'm going to speak about, I was asked to talk about scheduling circuits and error correction for subsystem codes. I broadened this out a bit to talk about scheduling syndrome measurement circuits in general. I think a lot of you are familiar with this, so maybe some part of this will be review. So I tend to, so let me just set the stage. I tend to think about this from the perspective of superconducting systems, solid state systems. So we have a programmable computer, and we can apply gates to a set of qubits. We have, some set of operations, measurements and resets, and the connections are fixed in this computer, and they're specified by some low degree graph. In most of our hardware today, these are all planar graphs, such as the ones you see on the left, the heavy hexagon graph or the square lattice. And I'll get the hang of this. There we go. And that makes a lot of sense because this is natural to engineer for the kinds of physical operations that we have. More recently, at least at IBM, we've been thinking about going slightly beyond this planar graph setting to a graph that could be described by a stack of planar graphs. So you have a fixed set of qubits, and then those qubits are connected by a graph that decomposes into a sum of planar components. And in particular, what seems most likely to be realized is one where we have a graph that's biplanar, so only 2 layers. And in practice, what this might look like, if you try to implement it, is that you have a chip of some maximum size, and on this chip, you can then wire somewhat long-range, non-local connections between sets of qubits. All right, and our goal, at least in the near term, is to think about measuring repeatedly checks of codes or checks of families of related codes repeatedly. And this is going to be a challenge that will be going on for the next several years to try to optimize this process and improve its error rate until we can see a definitive improvement in the code performance. Some examples are all well known. Planar codes, such as the surface code, the heavy hex code, which is something that is particularly well suited to the planar graphs, as well as subsystem codes and flocate codes. And on the right, we've already heard about the example of the bivariate bicycle code. But in principle, we could implement any codes where we can get the qubits close enough together that the couplers are kind of this W local, have a fixed diameter. All right, and let me just say a little bit more about this setting. So, for some up to some maximum size, we can have these on-chip, constant diameter connections to a very small number of qubits. We can imagine then putting these chips together on their edges, and then we can imagine taking collections of those and connecting them by longer range, say microwave interconnects. So when we talk about scheduling error correction on this, in this setting, we're really talking about, and I'm not going to say more about this here, but we'll be scheduling operations on a chip, but then we have this hierarchy of operations and timescales that we have to deal with. All right. And so measuring syndromes of codes may seem like a specialized operation, but it's the majority of operations that we'll be doing in the computer, and it's also part of a process that is applied to time-varying codes to implement logical operations. And all I'm really saying in saying this is, we know very well the idea of lattice surgery, which can be applied on all of these planar code settings. And then we heard from Stephen this morning about more generalized lattice surgery types of operations that can be applied to these more highly connected systems. And underneath all of these operations are, in some sense, this repeated syndrome measurement circuits for codes that change dynamically. And I mean, there are some exceptions to this I just mentioned, right? We'll want to combine these operations with a variety of other techniques in order to implement computation. And that includes taking advantage of symmetries of the codes, such as by swapping to implement permutations or by doing transversal gates. And there are more general and generalizations of them that may interact multiple qubits in the block at a time, as well as state injection for magic states. All right, so with that kind of introduction, I'm going to just define some of the objects that I'm going to use later in the talk. Again, many of you may be familiar with this, but if not, I'll describe it from the top. So we all know a stabilizer code is defined by a commuting group of operators. We'll write down a generating set for them, and then the code space is the +1 eigenstate. And then we know that we can choose a set of commuting operators to describe the logical qubits that are encoded in this code. And so in this case, we partition them into two sets. There are R qubits plus K qubits, right? And the way we describe a subsystem code is that we define a gauge group by taking the first R of these encoded qubits and bringing their logical operations into the gauge group. And now this is, these operations don't commute with each other, but what we're promised is that there's some low-weight generating set of this group that we can easily measure on the hardware that we have with the connections that are available. So that may mean that we've picked the hardware so that we can measure those operators, or it may mean that we have the hardware that we're given and we have to somehow make a mapping to it, right? But that's what we're promised. And then the code space is described by these dressed logical operators, and they have a corresponding code distance. And so those are all the parameters of the subsystem code. All right. So one important operation that you can do in subsystem codes that isn't available in just the stabilizer picture is one where we can take some of these gauge qubits, these unprotected qubits in the code, and we can project them onto a fixed state. So we can really pick any, imagine that you have these R qubits. I can put them into any stabilizer state I like by measuring a product of these gauge operators. And then I can fix its eigenvalue by picking an anti-commuting operator from that group and correct it, right? And it turns out that this procedure, which is, it's been known for a very long time, but it keeps reappearing in many places. So in particular, in understanding the process of lattice surgery, there's a subsystem code that's protecting the information during that process. In improving thresholds for subsystem codes, and also in some of these dynamical codes. All right. So again, everyone's familiar with this, so I'll move quickly. But we want to implement these operations. We need to write down circuits that measure them. This circuit is a bare measurement. We just use a single qubit, couple it, and measure the syndrome. Now, as we've already seen a couple different times, but I'll just say it explicitly, right? Faults occur in this circuit according to some noise model or according to some actual model in the device that we have to characterize and bring in. And when faults occur at certain points in the circuit, they propagate. And so, this set of errors that we get, these hook errors, occur at low order, but they, but they're high weight. So, this is detrimental to operating our code. And a couple technical points that are important is that this set of hooks depends on the gate order. So when we choose the order of these gates, the circuit may be equivalent, but its performance may differ. And this is also a function of the noise model as well. So there's something very subtle here to pay attention to. Also, these hooks should be considered modulo the gauge group. So in particular, if you put a bit flip right at the beginning here, you might naively say, oh, this propagates to W-1 of my qubits in the support, but I can multiply times gauge operators and reduce that weight. So that's just a weight one event. All right. Now, from this point forward, I'm just going to focus on CSS codes, right? So in this case, I can write the stabilizer as elements that are either all, have only X's in their support or only Z's in their support. Same for the gauge group. All right. So if we can find fault-tolerant circuits that are bare like this, that's ideal because we use few resources to make those measurements. But sometimes it's not possible to arrange for that set of hook errors to be in the correctable set of the code. And in that case, we may or may not want to do something else. And so in the case where we're measuring low weight checks, a good approach is to add flag qubits. Here are a few references, only some of the references for the work in this area. But just the general idea of the flag is that there are some faults here that lead to high weight errors. We would like to be able to localize them in the circuit and have some additional syndrome information to tell us when that event has occurred. And ideally, this extra flag bit will be enough to distinguish these and allow us to correct the error. Okay, I think I'm sorry. So I started at 1:30, and I have until 2. All right, thank you. All right, so let me just say a few words about the scheduling problem in general. And I'm going to use words rather than describing precisely what the scheduling problem is, because I think the problem you want to solve will depend on the specifics of your code. But what we want in general is we want a very shallow syndrome measurement circuit. And we want to use as few extra resources as possible to measure the syndrome. So that means few measurement qubits, few flag qubits, maybe even none. There are some examples where you can use none. Now, the resulting syndrome measurement circuit needs to be something we can implement. So it just means one operation per qubit per time. It also needs to be right. And so, these are 2 examples of correct parity measurements back to back. So these are 2 commuting operators for the 422 code. You can measure them one after the other, but you can also interlace them as long as you're careful. And it has to do with how many operations, you have to kind of push an even number of operations through. That's the intuition. And then finally, and this is what I think is particularly difficult, is that the circuit needs to be fault tolerant. And so the way I think about this is you want a large circuit level distance. And it doesn't necessarily need to be the full distance of the code, but should be close. And this is defined by the number of faults you can insert into this circuit that generate a logical error without triggering any detections. Okay, so now for the second half, I'm just going to talk about 3 examples. And I'm pulling these out of some different recent papers just to highlight some of the questions that come up with scheduling. The first example I'll talk about is this bivariate bicycle code. First, I'll tell you how it's defined. So it's a CSS code. It's not a subsystem code. And the X and Z check matrices break into a left and a right block, acting on left and right qubits. So if you draw the check bits, which correspond to the rows, and the qubits, which correspond to the columns, you get a tanagraph like this. And it has this structure. You can see the color coding to tell you the left and right qubits and the X and Z checks, and then the connections between them. If we choose A and B so that they commute, then this will give you a valid stabilizer code. And the way this is built is that you take A and B to be sums of powers of cyclic shift matrices. Okay, so I mean, maybe the details aren't too important here, but they have that form. And these different powers, A sub I and B sub I, can be picked however you like, provided that they give you a good code when you're done. And here's one example that I guess we've seen a few times already. All right, so for this code on the right, actually for the whole family, right? You can solve this scheduling problem. The goal is to optimize the depth of the circuit, and it turns out that the minimum depth you can find is 8. We have not been able to find a shorter schedule. In order to solve this problem, it's really important to use the symmetry of the code to simplify the problem. So this code is translation invariant in a sense, right? You can use the cyclic symmetry. And what you come up with is a whole set of schedules that are described kind of in this way, where in each layer we have some term in the polynomial that we're applying. And turns out there are many valid solutions with the given depth, but they're not all the same in terms of their performance. And so we need to pick circuits to give a large code distance. So this is like a second filtering step, and this is actually the hard part. So here, to do this, you have to quickly evaluate the circuit level distance for the example codes. Right, so just to remind you again, the circuit level distance on the left, right, the error at low P is going to scale like this. And so if we're operating at very low error rates, we almost certainly want to find high circuit level distances. In our case, the circuits don't preserve this distance. They get pretty close, but they don't actually have D circ equal to D. And so here are some examples here. And you can see also these are bounds. So the technique we're using, we're able to upper bound the distance, but we can't compute it. This may be in equals now. But yeah, it's very hard to know this. So this is a difficult problem. Now, how important is it? I'm not going to, right, so everyone's seen these plots. There's a logical error rate on the y-axis. There's a physical error rate on the x-axis, a family of codes, and the error rates are decreasing as the physical error rate goes down. As you increase the distance of the codes, you expect the logical error rate to decrease. And what I wanted to point out here is not the high-level message here, but the impact of this circuit level distance on the performance of the code. So there's an ansatz that takes this circuit level distance into account and fits the numerical data. And what you can see is this down here shifting away. And that conjecture is due to this decrease in the circuit level distance. But you might then say, well, look at the performance at 10 to the minus 3 or nearby. Does it matter? And I think that's kind of interesting, because my intuition has always been, certainly for small codes, we really want to have strict fault tolerance. And maybe this is really not necessary in practice at code distances that matter at the scale that we're interested for computing. All right, the second example I'd like to look at is this heavy hexagon compass code. So this is a subsystem code. It's defined by a gauge group on the left. One color is the X checks of the code. The other color is the Z checks of the code. And then the center of that gauge group is this stabilizer group, which is, all of the squares are surface code checks, and then the blue stripes are Bacon short code checks. Right? So it's an asymmetric code. And what is important is that if we want to map this onto the heavy hexagon code, to the heavy hexagon lattice, we have to mediate the interactions that are there through the extra qubits in the graph, right? And so, so here's an example of how to do that, right? The weight 2 operators are easy to measure. I apologize for the color change. The reason that this the reason this happened is that the code is asymmetric, and you might prefer to operate it one way or the other. In our hardware, we prefer to use the surface code side for phase errors. So anyway, but let's switch that picture here. These are the two circuits, and you can see we're using these intervening qubits here as flags. Let me say a little more about how this works. So this is an idea that was actually communicated to us by Ben Reichart, and we've been able to take advantage of it in our experimental work as well as our some of our simulations. It's called deflagging, and the idea is that if these faults on the bottom propagate to very low weight errors, then by acting on those flags locally, you can reduce the weight of the error so that a first order fault leads to a single error on the data. So in this case, you can see that if I look at how these faults propagate, I can come up with a simple procedure where if one flag or the other is raised, I apply a single qubit correction, and I'm left with only at most one fault on the data, right? So that makes these circuits strictly fault tolerant. And you don't actually have to apply these. You can just update your polyframe and push it forward. All right. So now those are the ingredients to the gauge operator measurements. But there's another idea that comes from work by Oscar Higgett and Nico Berkman called schedule-induced gauge fixing. The reference is here. And so on the left is a picture for a code that I haven't defined yet. It's the subsystem surface code. And you measure the stabilizers in the traditional way. So you measure all of the z checks and all of the x checks and so on, and combine them to compute the parities of the stabilizers, to form your detectors. And what they've observed is that if you repeat these measurements, what you can do, these gauge operators become detectors. And it turns out that this additional information is beneficial to the error correction process. And so I saw this result, and I wanted to see how this impacts the heavy hexagon code, and also how it impacts other codes that map to the heavy hexagon lattice. All right, so this is, again, same kinds of plots, increasing distance. It turns out that the optimal number of repetitions is 2. And just to provide some, I was curious if this was something that kind of kicked in asymptotically, or if it was something that we could take advantage of at low distances. And you can see that even for small distances, we get improvements in the logical error rate. And so, with this optimization, I wanted to see if we could further. So, right, you can see that as the logical error rate improves, as the distance increases, we're beginning to see less and less improvement in the logical error rate because this code has no threshold. And we're also beginning to see that the noise is becoming very biased toward predominantly X-type errors. And that's the Bacon-Shor code kind of failing at these high error rates. Right? There's an optimal error rate for the optimal distance for a given error rate. So can we do better by looking at a code that's more closely related to the surface code? And so for the last example, look at the subsystem surface code. Right? It's defined by the gauge group on the left and the stabilizer group in the middle, which is each stabilizer is a product of 2 of these triangles. And we're going to use the rotated form of this code, which uses, it uses fewer qubits than the code as it was originally defined with its original boundaries. All right, and now this code has a threshold, so it should perform better at higher distances. All right, so in the last couple minutes, let me just show you quickly how we map this onto the heavy hexagon lattice. Right, so you can see right away that one type of gauge operator is completely natural to measure. We can measure with a bare circuit. All faults that occur on all the hooks modulo the gauge group are weight 1. And then we have to use kind of a bridge technique for the Z-type gauge operators, but we can write down a relatively shallow circuit to measure them. Why is this distance preserving? I mean, you can argue essentially by enumerating the cases here. And what you find is that these circuits are distance preserving in the CSS sense. So if you put in W faults, you'll produce a mixture of at most, if you put in a single fault, for example, you'll produce at most 1 X error and 1 Z error, but they may be on different qubits. And the example you can see is here. So modulo the gauge group, this pair of z operators is equivalent to a z operator on the top qubit. And this is absorbed in, when I reset this qubit. In fact, it shouldn't even matter at all. Right. So that's roughly the reason. The rest of the gauge schedule is put together in a completely obvious way. So we only have enough resources to measure half of our z-type gauge operators at a time. So we do that. And then you can go into the, you can write down the specific circuits here. Doesn't matter. But what I would mention is that there are some additional detectors in here that we're not taking advantage of. So there are some qubits that should stay in the 0 state throughout this computation. And we're not looking at them at the moment to create additional detectors. I'm not sure if that would improve the result. What we find here, though, is the subsystem surface code on the heavy hex lattice has roughly a 0.3% threshold. There's still a slight bias in the noise. And we attribute that to faults that are occurring during the deep Z stabilizer measurements that then propagate forward. And so, putting this together, I was sort of surprised and honestly a little bit disheartened to find that these two codes behave nearly identically at small distances. That's just how it is. So schedule-induced gauge fixing has improved both of these things, but it hasn't made, hasn't given me a clear victory over the heavy hexagon code until we go to much higher distances. So once we get to about distance 11, then you can see that the fact that the subsystem surface code has a threshold begins to act in our favor. And I'll just mention for reference that there's also some recent work using ideas of time dynamics to map the surface code onto the heavy hexagon lattice. And here this seems to exhibit a comparable threshold as well. So I guess the conclusion of this piece here is that we have many ways of implementing planar codes. Having this library of ways to do this may be something that will be beneficial experimentally, because these circuits are not all the same in the details of their implementation and how often they reset and measure qubits. All right, and so I'll just wrap up. So this problem of scheduling these stabilizer measurement circuits is something I think is important. It's practical. And there are opportunities for creative optimization here as we go to implement these operations on our hardware. Some questions that have come from each of these examples. How important is distance preservation? Verifying that is difficult. How would we do this in cases where we don't have symmetry? I think that the next step here is to think about, and people are already doing this, but there are many practical constraints that come into this problem that I haven't talked about. And so I think that's an important area to work. I think the idea of modifying these subsystem codes to give them thresholds is interesting. I wonder if the heavy hexagon code can be modified in some way. And finally, I think it's important to move beyond just storing information and really thinking about computation next, and bring these ideas from subsystem codes into the computation picture. Thanks.
Are there questions? Yes.
So when you do the repeated checks measurements for subsystem codes to improve the thresholds, does that complicate the decoding at all?
So in this case, they were all decoded by minimum weight perfect matching in a way that was similar to the surface code. Mm-hmm. The pattern of detectors that you get differs as the schedule is no longer time translation invariant. It's time translation invariant in these chunks that have, just like you can see here. So actually, in the implementation, I wrote it so that you can write down any pattern of checks in any order, and it's possible to do that.
Can you maybe elaborate on how you performed the optimization itself? Like, did you try several options? And also, how did you evaluate? Did you do Monte Carlo simulations, or did you do some analytical analysis?
Yeah, I guess, so for the small flag circuits, I mean, there are many constructions now in the literature that you can find as good starting points. There's also in that case, kind of a brute force way of generating tables to check to see if the flag outcomes give you sufficient information. For the distance calculations, the technique that turned out to work really well was one based on right. So for that family of codes that I showed earlier, the bicycle codes, they're decoded by BP-OSD, a different decoder, and that the optimization problem that solves can be turned into a distance test that is really quite fast, and so we could run through many examples with that. But it just gives you good performance. To look for counterexamples, usually use integer solvers and write down some mixed integer program and then solve this to try to find counterexamples. In some cases, you can just prove then that the distance is what it is.
Yeah, just coming back to the scheduling problem for the bivariate bicycle codes. I was just wondering, how were you able to interleave the X and Z stabilizer measurements in the same circuit moments? Is there a general approach to doing that, finding valid circuits?
Yeah, I mean, I think this yeah, you can write down a set of constraints, which corresponds to this roughly, and then solve that.
Would that be like some sort of bipartite edge coloring on a graph sort of problem, or?
I mean, you can find examples of the specific constraints for color codes by Everland and Kubica. And just if you're looking for an example of the problem, I didn't write down the exact problem that's being solved here.
Okay, yeah, no, that's good enough. Thank you.
Okay, we have maybe time for one more question, if there's any.
Just a brief one. You mentioned that you had a preferred basis. This is kind of an experimental question, sorry.
Oh, yeah.
You had a preferred basis for like which side was sort of the surface code and which side was the Bacon Shore code. And I was curious why you made the decision to kind of switch it.
Yeah, so at the time, I guess we anticipated more correlated phase errors from our gates. So like coherent phase errors between non-adjacent qubits. And so switching the basis was a way of dealing with that. Now, I mean, Micah can correct me or completely contradict me in the next talk, or right now.
Thank you.
Okay, let's thank Andrew again for the nice talk.